cement, a gray, rough, and seemingly inexpensive powder, is the silent backbone supporting luxurious skyscrapers, massive infrastructure projects, and multi-billion-dollar highways for decades. But transforming stubborn mountain rock into this remarkable binding material requires a demanding engineering journey. It begins with earth-shaking quarry blasts, continues through gigantic crushing machines, and culminates in the intense heat of rotary kilns operating at temperatures high enough to fundamentally transform the raw materials. Today, join Factron Process as we go inside the factories to discover how this essential material is made. Few people realize that what once seemed to be nothing more than the ash left behind by volcanic eruptions laid the foundation for one of the most durable construction materials ever created. As early as 128 AD, the Romans were using volcanic ash to produce a form of concrete capable of surviving for millennia, allowing them to build structures such as the Pantheon and the Colosseum, which still stand in the heart of Rome today. Cement has become one of the foundations of the modern world. Every year, humanity produces more than 4 billion tons of cement to build homes, highways, dams, bridges, and sprawling cities. To achieve that scale, the industry consumes roughly 4.5 billion tons of limestone annually, forcing the extraction and effective removal of hundreds, if not thousands, of quarries across the globe. Yet this essential material comes with a significant cost. The cement industry is responsible for nearly 8% of global carbon dioxide emissions. The very material helping to build the future is also quietly contributing to the warming of our planet. The journey of cement begins at massive open-pit limestone quarries. Although cement is made from a mixture of minerals, limestone alone accounts for as much as 80% of the raw material blend. Because cement is produced in enormous volumes, but carries a relatively low value per ton, most cement plants are built close to quarries to minimize transportation costs. The process starts with geologists surveying and analyzing rock layers to identify deposits with the right calcium content. Bulldozers then strip away the overburden, clearing vast areas of topsoil, vegetation, and weathered rock to expose the hard limestone beneath. Once the deposit is exposed, controlled blasting operations begin. Giant crawler-mounted drilling rigs bore hundreds of blast holes more than 20 meters deep, penetrating rock at rates of up to 5 feet per minute. Workers load the holes with ANFO explosives and connect them using delay detonators, creating a carefully timed sequence of blasts rather than a single simultaneous explosion. When the warning sirens sound, technicians trigger the blast remotely. Within seconds, 5 tons of explosives bring down an entire rock face, breaking loose as much as 20,000 tons of limestone and turning the quarry wall into a vast field of fragmented rock. Quarries do not always become abandoned scars on the landscape once extraction ends. Thornton Quarry near Chicago, for example, has been partially transformed into a massive stormwater reservoir, serving the surrounding urban area. But when quarry operations are poorly managed, the consequences can be devastating. A quarry collapse in Cirebon, West Java, Indonesia, buried heavy equipment and claimed the lives of 17 people. From the sea of broken rock left behind by the blast, the production line begins bringing order to the material. Large hydraulic excavators move to the quarry face, loading multi-ton limestone fragments into mining haul trucks. The trucks then back up to receiving hoppers and dump their loads onto vibrating feeders, which regulate the flow of material into high-capacity hammer crushers. Inside the crushing chamber, heavy steel hammers rotate at high speed, repeatedly striking the limestone and breaking large rocks into smaller fragments through a relentless series of mechanical impacts. The crushed stone is carefully controlled to a size of just a few inches, typically below about 100 to 150 millimeters, making it stable enough to travel through conveyor systems and enter the homogenization process that follows. After leaving the crusher, the limestone begins its transition from quarry rock to a continuous stream of raw material feeding the cement plant. At facilities located close to the quarry, fleets of specialized haul trucks, each capable of carrying 40 to 100 tons per trip, operate continuously to transport limestone to the storage area. At larger production complexes, however, the plant does not necessarily need to be built next to the quarry. The modern solution is the use of heavy-duty conveyor systems that can move material continuously across challenging terrain, crossing hillsides, steel bridges, and enclosed corridors stretching for dozens of kilometers. This technology reaches an extraordinary scale at Fengkai, China, where RBL REI constructed 2 parallel limestone conveyor lines extending a combined distance of 40 kilometers, setting a world record for the longest limestone conveyor system ever built. Another remarkable example is the 17-kilometer conveyor serving the Lafarge-Surma cement plant, which transports limestone from India into Bangladesh. It is widely recognized as the only conveyor system in the world that crosses an international border, carrying approximately 960 tons of limestone per hour between 2 nations. Once at the plant, the crushed limestone is conveyed directly into a preliminary homogenization storage facility, typically built as a long stockpile hall or a dome-shaped structure. Here, a stacker continuously deposits the limestone in multiple layered rows, while a reclaimer extracts the material across the full cross-section of the pile. This approach blends limestone from different quarry batches, reducing fluctuations in calcium content and creating a more consistent raw material supply for the cement manufacturing process. Leaving the homogenization storage, the limestone enters the blending stage. Limestone, clay, silica, and iron ore are fed into dedicated storage silos. At the base of each silo, precision weighing systems operate with extreme accuracy, ensuring that every material flows into the process according to a carefully controlled recipe. The blended materials are then fed into a vertical roller mill, combining grinding and drying in a single operation. This technology can reduce power consumption by 20 to 30% compared with traditional ball milling systems. Massive grinding rollers apply enormous compressive forces, reducing the rock into a fine powder measuring less than 90 microns, while achieving production rates of 100 to 500 tons per hour. The raw meal then passes through a separator, where coarse particles are automatically returned to the grinding table for further processing. Throughout the entire operation, a SCADA control system continuously monitors and regulates everything from temperature to particle fineness, ensuring a highly uniform raw material before it enters the kiln. Hundreds of tons of raw meal per hour enter one of the most energy-efficient systems in modern cement manufacturing, the preheater tower. From the silo, the material is lifted to the top of the preheater tower and falls through multiple cyclone stages, where it comes into contact with hot gases rising from the rotary kiln below. Through this heat exchange process, the temperature of the raw meal can reach around 850 degrees Celsius before entering the main burning zone. The material then moves into the calciner, where fuel is burned to drive the near-complete decomposition of limestone and release most of its carbon dioxide. This greatly reduces the thermal load on the rotary kiln and improves the efficiency of clinker production. Today, many cement plants also use RDF, discarded tires, and biomass to replace part of their traditional coal consumption. In Europe alone, alternative fuels already provide more than 40% of the thermal energy required for clinker production. Leaving the calciner, the raw meal enters the hottest part of the entire plant, the clinker kiln. This massive cylindrical steel shell can extend nearly 260 feet in length. Lined with refractory bricks, it is installed at an incline of roughly 2.3 to 4 degrees and rotates slowly at speeds ranging from 0.6 to 4.5 revolutions per minute. As the kiln turns, the material gradually moves from the higher end to the lower end, advancing deeper into a thermal zone exceeding 2,700 degrees Fahrenheit, while the flame at the burner can reach temperatures of around 3,600 degrees Fahrenheit. At these temperatures, the raw meal does not melt completely like metal. Only about 20 to 30% of the material enters a liquid phase, just enough for the various oxides to react, agglomerate, and recrystallize into clinker. Within these glowing red nodules are alite, belite, and palite, aluminate, and ferrite, the mineral phases that determine the strength, setting behavior, and binding performance of cement. The material leading the kiln is incandescent clinker, typically in the form of granules or small nodules measuring about 3 to 25 millimeters in size. This stage is also responsible for the largest share of carbon dioxide emissions in the entire cement production process. When clinker leaves the rotary kiln, it is still glowing red hot, with temperatures exceeding 1000 degrees Celsius. At this stage, cooling too slowly can allow the newly formed mineral phases to continue changing, directly affecting clinker quality. To prevent this, the stream of incandescent material is immediately transferred into a grate cooler system. Inside the cooler, the clinker is evenly spread across a heat-resistant grate, forming a material bed approximately half a meter thick as it gradually moves toward the discharge end. Powerful fans beneath the grate force high volumes of cool air upward through the clinker bed, extracting heat from each glowing particle and rapidly reducing the material temperature to below 100 degrees Celsius. What makes this system particularly effective is that the enormous amount of heat is not wasted. After absorbing thermal energy from the clinker, the air is heated to several hundred degrees Celsius and is then recirculated back to the rotary kiln and calciner to support fuel combustion. As a result, the grate cooler not only cools the clinker, but also recovers a significant portion of the heat that was just generated, improving energy efficiency and helping the entire production line operate more efficiently and consistently. After thermal stabilization, the clinker arrives at its final stop, the cement mill. Here, the rock-hard clinker is precisely blended with 3 to 5% gypsum, a critical ingredient that controls the setting time of cement and prevents it from reacting too rapidly when mixed with water. Additional materials such as fly ash and blast furnace slag may also be added to improve performance and reduce the clinker content. Inside the mill, tons of steel grinding media continuously collide with, crush, and grind the clinker into billions of fine gray cement particles, measuring only a few dozen micrometers in size. This is one of the most energy-intensive stages of the entire process, accounting for up to 40% of the plant's total electricity consumption. Once these particles reach the required fineness, they are no longer rock. They have become cement, a material ready to undergo remarkable chemical reactions with water, forming the strong structural foundation that supports the modern world. Before cement can be shipped, it must pass a series of rigorous quality control tests. From the storage silos, automated sampling systems continuously collect material and deliver it to laboratories for analysis. Specialized instruments verify chemical composition, fineness, setting time, and compressive strength to ensure that every batch meets strict technical specifications. This level of control is essential because even minor variations in material properties can create major problems years later. Issues such as alkali-silica reaction can slowly cause concrete to expand and crack from within, reducing the long-term durability of structures. Today, many cement plants rely on automated laboratory systems such as POLAB, which can collect samples, prepare them, and perform analyses almost continuously with minimal human intervention. As a result, every batch of cement is monitored around the clock before it leaves the factory, helping ensure consistent quality and reliable performance in the field. When the cement has passed all quality requirements, it moves to the packaging area. Here, operators work alongside automated packing machines. Empty bags are placed onto filling nozzles, and with a single motion, cement flows rapidly into each bag. Precision weighing systems ensure that every bag is filled to exactly 50 kilograms. In many modern plants, even the bag handling process is fully automated by robotic systems, allowing hundreds of bags to be filled every hour with remarkable consistency and accuracy. Once filled, the bags are automatically released onto conveyors and sealed by stitching or heat sealing systems. As the bags move along the conveyor line, intelligent sensors continuously monitor weight, bag condition, and seal integrity, removing any defective products before they proceed further. The bags then enter an automated palletizing system. Robotic arms operate in a carefully coordinated sequence, stacking each bag onto pallets with the precision of laying bricks. Alongside bagged cement, a significant portion of production is shipped as bulk cement. From storage silos, the cement powder is loaded directly into specialized tanker trucks through enclosed loading systems and pneumatic conveying equipment. This method reduces packaging waste, lowers handling costs, minimizes dust emissions, and is ideal for concrete batching plants and large construction projects, where the cement can be transferred directly into storage silos before being mixed with sand, aggregate, water, and other additives. And so ends the remarkable journey of cement. From raw limestone extracted from the earth, to blazing kilns and modern laboratories, to the finished material that helps shape the world around us. The cement manufacturing process stands as a testament to humanity's relentless ingenuity in creating the foundations of modern civilization. Every particle of cement leaving the factory represents a commitment to quality, reliability, and safety. Bridges and cities that endure for generations. Yet the most fascinating part of the story is this: cement only truly comes to life when it meets water. What chemical reactions transform this fine gray powder into a material strong enough to carry enormous loads and withstand the passage of time for decades?